Karthik, is it audible? Hello?
Yes, sir.
Nagaraj MS, are you there?
Yes, sir.
Yeah, very good morning. Yeah, so we have 6 participants right now. Shall we wait or shall proceed? Hello? Vinay ji? Vinay, are you there?
Yes, sir.
Yeah, fine. So until other participants join, we shall start. Yeah. So in the last period, we were dealing with the multi-programming operating system. So multi-programming operating system, as name itself indicates, multiple number of programs. So the OS will be having so many user programs. So multiple programs are being maintained in the memory of the computer system at any time. Hence the name multi-programming operating system. So the computer system will be having multiple number of user programs or processes, so which can run simultaneously. Hence the name is being given as a multi-programming operating system. And so the main intention behind the development of this multi-programming operating system is to have efficient resource utilization. Okay, so what do you mean by this efficient resource utilization is, suppose if in any computer system, if I'm only maintaining a single program, okay, so that single program will be having only, I mean, that single program can utilize only limited number of resources. So the other, I mean, other resources will be simply wasted. So to make use of the computer resources effectively, I can I can maintain more number of programs, or I can maintain a sufficient number of programs, so which can run simultaneously. Hence, the computer resource will be effectively utilized. And second point is, so this multi-programming operating system will be employing something called as a DMA mode of input-output operation. Okay, so like it can perform IO operations of some program while using the CPU to execute some other program. So we can have the effective program mix. Okay, so when dealing with multi-programming OS, don't forget these predefined words like mm, appreciable program mix. Okay, so we have seen different types of programs as well. So we have so-called CPU bound programs and IO bound programs. Along with the definitions, like we have seen that CPU bound programs, CPU bound programs will be having a lot of computations, a lot of calculations, or the so the work of CPU will be more, and we have few number of IO operations when compared to the IO bound operations, IO bound programs. Okay, so these IO bound programs will be having little computations, I mean, less number of calculations are involved in IO board programs, where and the more number of IO operations are involved. And so regarding the word DMA, so this multi-programming OS will be using something called as a DMA mode of IO operation. So that so word DMA is being explained using this particular figure, where we can have the direct interaction between the memory and the disk, or from disk to memory. Any information, any data can be transferred from either memory to the disk, or from say disk to memory directly without having the use of CPU. Hence, the CPU can be used to execute say some other process. Okay, so the CPU involvement is not there in the information transfer between memory and disk, or from say disk to memory. Hence, I can make use of the CPU for other process or other program execution. So we have so this use of DMA mode of input output operation in the multi-programming operating system. So we have seen these slides, and like in the last class, like we also saw how multi-programming OS will be able to handle the different processes in a system. Okay, like along with these three figures, so we have the switching from IO operations to a CPU and from CPU to IO operations. Okay. So regarding the priority of programs, so we have seen the degree of multi-programming as well, where we need to have a sufficient number of user programs, user processes in the memory, so as to achieve a higher degree of multi-programming. I need to have appreciable sufficient number of user programs so that I can keep CPU very much busy. Means we need to avoid the ideal time of CPU. I cannot simply give some rest for CPU. My CPU should be always executing so one or the other programs. Hence, I should be able to maintain sufficient, okay, sufficient or appreciable number of user programs in the memory. And once I say user programs, means again I can have IO bound programs as well as CPU bound programs. So I should be able to maintain a uh, right program mix, we say. Okay, so the like the programs which are present in the memory, so those programs can be of type CPU bound programs as well as IO bound programs. Yeah, so last like we had stopped at this particular slide. Now coming to the present class. So is this slide visible, audience? Is this slide visible, participants? Are you seeing this particular slide?
Yes, sir.
Yeah.
Yes, sir.
Yeah, fine. So what is the explanation of this particular slide is, like with respect to the multi-programming system, like we had, like we know the meaning of IO bound programs and CPU bound programs. I repeat, IO bound programs are nothing but the programs, so which involves more number of input and output operations. So for example, like I want to say print hello world 100 number of times. Okay, so like this program involves more amount of IO operations. Why? Because so for printing hello world, like I need to go for use of a screen or a monitor. Hence, like, this particular C code will be involving more amount of IO operations. So whereas the computation is very much less in the printing of hello world program. Why? Because simply like the computations or the work of CPU is to execute the program, and more work is for the displaying function, right, of hello world. Hence, this program involves more input output operations and less computations. So when compared to the CPU bound programs, for example, so these CPU bound programs will be having a more amount of calculation, more amount of select more amount of computations when compared to the input and output operations. Okay, so here, so by keeping the definitions of IO bound and CPU bound programs, so let us discuss this. So the basic point here is, in multi-programming environment, an IO bound program should have higher priority than a CPU bound program. So suppose if I have here two programs where PROG program IOB is a IO bound program, and here is program CB. CB is the CPU bound program. So here if I have two programs where first program is the IO bound program, which involves a lot of input output operations and less CPU computations, less CPU activity. And if you have a second program, like which is like so-called program CB, where this program CB is CB bound program, which involves a lot of computations, lot of calculations, and less IO activity, right? Like in this case, always the highest priority will be given for IO bound programs. So this is the concept here. Okay, and this particular concept is being proved by using this timing chart, where we can see two programs. One is IO bound program, and second one is program CB. Program CB is the CB bound program. Okay, so suppose if I'm executing the IO bound programs, the so-called IOB program, right? Like as the definition itself says that this IO bound program will be having a very less CPU activity, say from 0 to T1. If you're like seeing the slide, say from 0 to say T1 amount of time, we have very less CPU activity and the program is involving lot of input and output operations or input and output activity. Okay, so like in this case, you can see that this IO bound program will be having more amount of IO activity, and the CPU utilization for calculation is very much less. Okay, so while the IO bound program is busy in doing the IO activity, I cannot keep the CPU idle. Hence, what I can do is I can execute a CPU bound program, and this can be seen in the CPU activity where where the like here the CPU is being utilized to do more calculations. Hence, while this IO bound program is doing the IO activity, I cannot keep the CPU idle. Hence, I will switch over to the execution of CPU bound program. And as you can see that here is the CPU activity that is being done from T1 to T2. Okay, so upon the finishing of IO activity, right, I can have the execution of the CPU programs or the CPU bound programs. And once the finish of IO activity is there, means again I can execute the IO bound program. And as we know that IO bound programs will be involving less amount of CPU activity and more amount of input output operations. Hence, same thing is been shown here. So this IO bound programs will be having less CPU activity and more amount of IO activity. Okay, hence this line is shorter and this line is longer. Okay, again same statements. If the IO bound program is doing a lot of IO activity, means again I cannot keep the CPU idle. Hence I will again switch over to the CPU bound programs. Hence until the IO activity is been completed, I can keep the CPU busy in carrying out the system calculations or computations. Okay, and this thing repeats. So, but the main thing what I can notice here is, like, even though we are saying that IO bound program should be given higher priority when compared to CPU bound programs. Okay, so this particular line can be observed here. Okay, even though we have the highest priority given for the IO bound programs, so but still we are engaging the CPU. Okay, even though IO bound programs are having higher priority, even then I can also achieve, or I can also achieve a much more job from the CPU. Okay, so this particular concept has been proved using this timing chart. Okay, and the second thing to be noticed is say from time period from T6 to T7. Do you hear some noise? Some noise. So all of you go for mute mode. Please mute. Second thing to be noticed here is, say from period T6 to T7. So what is happening here is, like in the time period T6 to T7, no operation is done by CPU. See here and here, no CPU activity is being performed by both the programs. Why? Because both the programs are waiting for the IO operations. So this particular point, as well as the IO programs which are given highest priority, it can be explained using this particular timing chart. Participants, please mute yourself. All the participants, please mute yourself. 4JD 18EC 56. Yeah. Is it audible? Is it audible now?
Yes, sir.
ಅದು ಯಾರೋ ಮ್ಯೂಟ್ ಮಾಡಿರಲಿಲ್ಲ ನೋಡಮ್ಮ. Yeah, Anup. Yeah. So now it's clear, I think. Fine. So what is the bottom line here is, using this particular timing chart, what we are showing is IO bound programs, right, should be given highest priority when compared to the CPU bound programs. And this concept is being explained using this timing chart. Okay, and what is explained here is like regarding the activities of CPU and IO activities, and don't forget to mention this particular point as well in the time period between T6 to T7. So here the CPU activity of both the programs are nil. So no CPU computations is been performed in the time period from T6 to T7. Okay, so also explain this. Yeah. Right. So whatever like we have discussed here, same thing is been tabulated like in the form of a table, and heading for this is techniques of multi-programming. Like as I told, you should be also concentrating on the heading. Okay. So whatever the heading that are being given in your prescribed book, so based upon the heading in the examination, the evaluator will be expecting the same theory concepts like in exam also. Hence the heading for this is techniques of multi-programming. Okay, so like an examination, like if they ask you to explain with relevant concepts that the like say different techniques of multi-programming, so then don't forget to use the word appropriate program mix and priority based preemptive scheduling. So like we have seen in the earlier slides also the meaning of the so-called CPU bound program and the meaning of IO bound program. Okay, so whatever we have discussed in the last slide, same thing is being tabulated. Okay, so let us see the first point. So the technique is appropriate program mix. Okay, so what we know regarding appropriate program mix is in the memory, the kernel is able to keep a perfect mix of CPU bound programs as well as IO bound programs in the memory, where like the meaning of CPU bound program is nothing but the program which involves a lot of computations and very little IO operations are involved, right? So this CPU bound program will be using the CPU in long burst. Okay, so the use of CPU is more in the CPU bound program, right? That is, it will uses the CPU for a long time before starting the IO operation. Okay, the same thing like we have discussed in CPU bound program. And regarding the IO bound program, like we know that like as name itself indicates, so this IO bound program will be involving a lot of input and output operations, but very less computation work. Okay, or very less calculative work will be there in the programs of IO bound programs. Okay, so these IO-bound program involves very less computation and more, a lot of IO operations are involved, means it uses the CPU in a small burst. So the use of CPU will be less in the IO-bound programs, and the use of CPU is more in the CPU-bound programs. So second technique is the priority-based preemptive scheduling. So what this like words indicate is like every program is assigned a priority. Okay, so whatever programs that we have in the ready queue for all the programs, okay, right, I need to assign some priority, and the CPU will be always executing the program which has got the highest priority. Okay, so let's say suppose if a program is executing, right? So for example, say any process or program P1 is executing on the CPU, and if any other program having the highest priority than the currently running program occurs, so then what CPU does is the CPU will halt the current program and the resources will be allocated from low priority program to the currently high priority program, and now the CPU is able to execute higher priority programs. Okay, hence the resources will be preempted. Okay, again the word preempted refers to the forcible deallocation of resources from any process and allocating the same resource to another process. That particular process we call it as the preemption. Okay, so here the basic point is always the CPU will be executing the program or the process which has got the highest priority, right? So when compared to, let's say, any two process having low priority and high priority, always the preference will be given for the higher priority process. Okay, yes. So you can explain these points for the techniques of multi-programming. So next is architectural support for multi-programming. So for this also in the examination, the question will be with the relevant concepts, explain the concept of architectural support for multi-programming. Hence, I'm keep on saying also do keep an eye on the heading and under uh, any heading, okay, like so what all been explained, right? In that regard, like so now the present heading is architectural support for multi-programming, and under this particular heading of architectural support for multi-programming, so we have these many features and the explanation. So the first feature is DMA. Like, as we know that according to the previous slide as well, like as we have discussed, so we have the use of DMA mode of input and output operation in case of multi-programming operating system. So what do you mean by this? So for explanation of this DMA, okay, like here we have used the same figure what we have dealt in the last slide as well. Okay, so we can have the interaction between the memory and the disk or from disk to memory without the involvement of CPU. Okay, suppose if I go for the programmed IO means of transfer, information transfer means here the CPU will be involved in the data transfer between memory and the disk. So, but here in case of DMA, okay, like as you can see here, in case of direct memory access, here we can have the information transfer, data access can happen between the disk and the memory or from memory to disk without the use of CPU. Okay, so this means that I can make use of this particular CPU for some other process execution. Hence, we are like here we are not involving the CPU in the data transfer between any memory and the disk or from disk to memory. Hence, this sort of information transfer, data transfer, we call it as direct memory access. And this particular technique will be used in the multi-programming concept. Means the CPU initiates an IO operation when an IO instruction is executed. So the DMA or direct memory access implements the data transfer involved in the IO operation without involving the CPU, right? Underline this, without involving CPU, and raises an IO interrupt so when the information transfer is completed. Wow. Okay. So next feature is memory protection. Let's call memory protection. So a program can access only the part of memory defined by the contents of the base register and size register. So the program is able to access only the part of memory that it is authorized to access. Okay. And third feature is the kernel and user modes of CPU. So we have basically two modes of operation of any processor. So one we call it as the kernel mode and second one is the user mode. So in the starting slides of this particular OS subject, so in the first class itself, we had dealt regarding the kernel mode of operation and the user mode of operation, where the kernel mode will be always having a higher privilege, higher rights, higher privileges, okay, higher options when compared to the user mode of CPU operation. So certain instructions called privilege instructions can be performed only when the processor or CPU is in the kernel mode. Like I said, when compared to the user mode of operation and kernel mode, always the kernel mode will be having the access to the privilege instructions and no user is allowed to access the so-called privilege instructions. So a program interrupt is raised if a program tries to execute a privileged instruction when the CPU is in the user mode. Okay. So like what is the bottom line here is if in the examination, if they ask you to explain the architectural support for multi-programming, don't forget to make use of this particular table. Also for the DMA, you can make use of these figures, okay, using which you can explain that. Like in case of DMA, we can have the data transfer between the memory and the disk, okay, without the involvement of CPU. Hence, this main resource, so-called CPU can be utilized for execution of other process, and I can keep this resource very much busy. Okay, and I can avoid the use of CPU in the let's say simple data transfer applications. Okay, so next we can call it as the performance of multi-programming system. Okay, so we have here a simple graph. Okay, so drawn so by taking the degree of multi-programming along x-axis and the amount of work done per unit time. Again, don't forget that the amount of work done per unit time. So per unit time we call it as throughput. Why? Because we know that any factor, any concept, any entity that is being measured with respect to time, that particular parameter or factor will be called as throughput. Okay, so here under the heading of the performance of multi-programming system, okay, so we can say that suppose if I'm able to maintain appropriate appreciable program mix, right? Again, the word program mix indicates what? Program mix is nothing but the mixing of IO bound programs and the CPU bound programs. Means whatever programs we have inside the memory for execution by the CPU, okay, those programs must be having a mix of IO bound programs as well as the CPU bound programs. So here the concept is, so when we are able to have the appropriate mix of IO bound programs and CPU bound programs, an increase in the degree of multi-programming would result in an increased throughput. Okay, suppose the program mix is say well, okay, suppose if the program mix is appreciable, so then upon the increase of multi-programming, I can achieve the increased throughput also, and this is neatly explained using this particular curve. Okay, like as you can see here, as we increase the number of programs present in memory, say from 1 to 2 to 2 to 3 and 4 and so on. Okay, accordingly the throughput is also increasing, and this increasing is not a linear curve. Okay, right, up to certain level you can achieve this, not right, not a problem. Okay, up to certain limit of increase of number of programs in memory, you can achieve the increased throughput. Okay, so but this does not hold good if I have more and more and more and more number of programs. Okay, why? Because the throughput is almost becoming constant after certain level of number of programs. Okay, right, so we can explain this, the variation of throughput with the degree of multi-programming. Again, the definition for this word, like so-called degree of multi-programming means what? The number of user programs that are there in the memory. And I also said that we need to have appreciable number of user programs in the memory so as to keep the CPU very much busy. Why? Because you cannot expect the valuable resource, so-called CPU, to be idle. Hence, what we can do is I can keep my CPU busy by offering the CPU with more and more processes or more and more programs. So that particular number of programs that are present in the main memory, that can be called as degree of multi-programming. Okay, and this graph is indicating the like the relation between the degree of multi-programming with the increasing throughput, and this increase is not having a linear relationship. Okay, so this increase of throughput upon increasing the number of programs, right, is achievable up to certain extent. So but once we have say like huge programs, more and more programs in the main memory, okay, you cannot achieve the increased throughput. Why? Because after certain level this throughput is becoming almost constant. Okay, like this can be explained for this particular graph. Fine. So next one is time sharing operating system. Regarding time, so what is the time now? We need to finish at 9:30, right? What is the time now? Yeah, so we have 10 minutes. Yeah, we have 10 minutes. Fine. So let me have the completion of this time sharing systems as well. Like as the name itself indicates, this time sharing operating system means what? The time. So what time is it? CPU time. So this CPU time, like which is the main resource of any computer system, this CPU time is being shared among n number of processes. Okay, so like this statement is been underlined. Why? Because we know that um, like any CPU, any processor will not be busy in just executing only one program. Okay, suppose if I have a situation where the CPU is just busy in executing a single program, so then it is of no use. Why? Because CPU has to give fair service to all the user programs or all the user processes. Hence, what can be done is the CPU time will be shared among n number of processes such that each process will be getting some fixed amount of CPU time for all the processes. Okay, so here all the processes will be getting equal amount of CPU time, and that particular slot of CPU time or that particular timestamp we call it as the quantum time. Okay, so the minimum amount of time that each process will get to execute on CPU, that particular small amount of time stamp, we call it as quantum time. Okay, so why this? So why CPU time is being shared among n number of processes is why? Because the main aim of operating system is to give the fair service, good service to all the processes. Hence, I can execute more than one number of processes on the CPU or on any processor. So this time sharing operating system is also called as multitasking operating system. Don't forget this. Hence, I have indicated here a star. Okay, so you can notice that. Okay, so you can see this. So the time sharing operating system is also called as multitasking operating system. Why? Because like again the word multi indicates many. Tasks can be the processes or programs. So here at a time I can execute more number of tasks. At a time I can execute multiple number of tasks. Okay, on the CPU. So for example, suppose if I have here 3 tasks. Okay, so which are currently running on the processor. So for example, one process can be the typing work, say like in the Word document, and second process can be the listening of music, right? Say like on the VLC player or the COM player, right? I can listen to the music. And third process is, say for example, like I'm seeing some photos, right? So suppose if these 3 processes are running right on the processor, so like the real thing is like all the processes will not be allocated CPU, right, until they are finished. Instead, so what will happen is the CPU will be switching from one task to another task, and as a user, we feel that our programs are executed continuously by the CPU. So, but the real thing, what will happen is the CPU will be switching from typing so-called typing task to the music task, again from music task to the like seeing the photos task. Okay, so the CPU will be switching from one process to the another process. Okay, hence the user feels that I can execute more number of tasks simultaneously on the processor. Okay, and second point here is, so for a certain time particular resource is allocated to particular process. Okay, so once that particular time slot is over or elapsed, so then the resource will be deallocated from the process and same resource will be allocated to the another process. So what this statement says is the resource for any process will be allocated only for particular amount of time, say 2 milliseconds. Okay, so once the 2 millisecond is over, so then the resources will be taken back from the process, and again same resource will be given for another process. Okay, so this OS will share the different resources on timely basis, and here with respect to the time sharing or like operating system, main point here is CPU time Okay, CPU time will be shared among n number of processes so as to give fair service to all the processes. An example is like I'm doing the typing operation and I'm also listening to the music and also I'm seeing some photos on the computer. So these tasks can be run parallelly. These tasks can be simultaneously like being done on the processor. So, but the real thing, what will happen is the CPU will be switching from one task to another task or one process to another process, like in a much more faster way. Hence, the user feels that all these processes will be executing concurrently. So, but that will not be the case in the real working of the processor. Okay. Next slide. Yeah. Right. So for example, say if P1 process needs 10 seconds of computation time, and we have here one more process so called P2, so which needs only 5 seconds of CPU time. Okay, like even though the second process so called P2 is in need of only 5 seconds for its execution, so the second process has to wait until we are done with the execution of P1. Suppose if I use this particular approach means second process will have to wait for 10 seconds of time until the first process P1 is completed. Okay, so to avoid this, what can be done is I can make use of time sharing operating system where the CPU time will be shared among a number of processes so as to serve maximum number of processes. So we can go for a use of a scheduling technique where the CPU time can be scheduled among a number of processes. Okay, that means what? Simply I'll be putting a timetable for the CPU time. Okay, so that each and every process will be allocated a fixed time period for each and every process, and that particular fixed time slot we call it as time quantum, right? Now the quantum time. So the scheduling technique can be used by the time sharing kernel, and this can be called as round robin scheduling with time slicing. So we have a figure to explain this round robin scheduling with time slicing, and here is the figure for it. Yeah. Okay. So but say before going to this figure, so like we can discuss still more points regarding the time sharing operating system. Okay. So we have a simple example here. So we have here say four process. So P1, P2, and P3 and P4 process, where the execution time for P1 is 4 seconds and execution time for P2 is 2 seconds and so on. Okay. And the time quantum is been fixed to 2 seconds. As time is running out, so like I'll stop right here. Okay. So I'll stop right here and let me continue this in the next class. Okay. So like all of you can log out and I repeat again, do say study these slides and do log in the right time. Okay. So you can revise the things like using slides or so by seeing the videos, and I'll be mailing you the link of all the videos. No need to worry. All right. Are you there?
Yes, sir.
Yes, sir.
Okay, pa. So you can log out. Thank you.